since its launch by NASA in 1977. Voyager 1 has been traveling through space for 45 years and has finally reached the edge of our solar system. This has been long anticipated, but contrary to what scientists have always believed, the space probe just found something truly unexpected at the so-called edge of our solar system, leaving everyone with more questions than answers. What did Voyager 1 discover? Join us as we reveal Voyager 1's impossible discovery after 45 years in space. During the interstellar expedition, the Voyager probes hit a significant milestone when they got to the part of space known as the heliopause, which is the boundary separating the Sun's influence from the vast expanse of interstellar space. Now, bear in mind that the exact position of this boundary had long been a subject of debate. But thanks to the projections of astronomer Bill Gurney in 1993, it was estimated to lie between 116 and 177 astronomical units, and each O is equivalent to the distance between the Earth and the Sun. Gurney's estimations were proved to be in point when Voyager 1 reached the heliopause approximately 2 decades later, detecting the expected rise in plasma density. Here's where the intriguing puzzle emerged. Despite the increase in plasma density observed by Voyager 1, there was no significant change in the ambient magnetic field direction. This was unexpected because a transition from a region where the magnetic field originated from the Sun to one where it came from other stars should have caused a noticeable shift. But no such thing was witnessed. Scientists probably thought Voyager 1 was the problem. But Voyager 2 further added another layer of mystery to the puzzle when it reached the heliopause at the same distance as its twin, but failed to detect any magnetic field changes. These unexpected observations posed challenges to theoretical models depicting the behavior of the heliosphere and how it interacted with the interstellar environment. The prediction that there was a synchronization between the heliosphere and the Sun's 11-year cycle did not align with the data gathered by the Voyager probes. Additionally, the solar wind, which fluctuates with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause, suggesting that the predicted position of the boundary should have been further out than 120 O. But it's not all hopeless, since the data collected by the Voyager probes has been instrumental in refining theoretical models. Because of the Voyager's discovery, scientists now believe that our Sun has moved from a hot, ionized zone to a partially ionized section of the galaxy, likely triggered by nearby supernova. These exploding ancient stars heated the surrounding area and removed electrons from adjacent atoms. The boundary between these regions can be likened to a turbulent seaside, characterized by mixed magnetic fields and small-scale changes near the heliopause, while negligible variations occur on larger scales. As what would become of the Voyager probes, their paths separated, with Voyager 1 heading towards the constellation Ophiuchus and Voyager 2 making its way to the constellation Cetus. While some scientists predict that the probes will have their demise in 2030, they could potentially endure for millions of years, outlasting our species. Perhaps one day, they will encounter other star systems, carrying with them the golden record, a time capsule of humanity. But the Voyagers didn't just fly into outer space on their own. They were sent out with missions that had a lot to do with the future of humanity. Exploring the deep depths of the cosmos after the United States lost the robotic race to the moon against the Soviet Union in the 1950s, the focus of space exploration experienced a shift. The moon and space dominance were still incredibly appealing, so attention turned towards a more popular and well-funded manned program. During that time, unmanned exploration was pushed to the background to take on a supporting role, with missions like Ranger and Lunar Orbiter paving the way for future Apollo missions. However, the idea of exploring other planets captured the imagination of many, coming in second only to the excitement surrounding the Apollo missions themselves. As a result, exploration programs naturally gravitated towards the next step, exploring other planets. Looking back, some people tend to overstate the scientific importance of unmanned programs compared to the political and technological goals of manned flights. They argue that the robotic missions were more scientifically pure in design and intent. downplaying the scientific achievements of manned missions. But the fact is, the promise of capturing photographs of the planets was what truly captivated and ignited the passion of the American public. The prospect of seeing those spectacular images sparked the greatest interest and enthusiasm during the golden age of space flight. Magnetospheric physics and gravimetric studies are indeed important, and their importance cannot be denied. But it was the quest for planetary photographs that truly resonated with people. The dream started to become reality on September 5, 1977, when a spectacular spacecraft was launched from Cape Canaveral, Florida, which is renowned for its testing of missiles and space probes. This event marked the beginning of an incredible journey as Voyager 1, a spacecraft, was launched into space. Interestingly, Voyager 1 wasn't launched first because, just 15 days earlier, its twin, Voyager 2, had taken off on the same cosmic adventure. Their mission was to explore Jupiter and Saturn, the gas giants of our solar system, along with their unique moons. What nobody thought was that these intrepid explorers would surpass their initial goals and venture to the farthest corners of the celestial horizon. The Voyager twins were equipped with cutting-edge technology, even by the standards of their time. From their engines to their propellers and antennas, everything was meticulously designed for durability. NASA got its inspiration from the Mariner spacecraft, but added some interesting modifications. The accomplishments of these Voyager probes have been nothing short of spectacular. More than 40 years ago, their early observations of Jupiter and Saturn's moons left researchers amazed, as they watched their preconceived notions about these distant worlds shatter before their very eyes. Earlier, it was thought that the foreign moons were desolate and pockmarked like our own moons, but scientists belatedly found them to be teeming with geological activity. Voyager 2, in particular, achieved several remarkable milestones during its journey. In 1986, it became the first spacecraft to pass by Uranus, and only 3 years later, it conducted a flyby of Neptune. Voyager 2 stands as the sole spacecraft to have embarked on such a path to this day. As these resilient spacecraft continue their unique voyage, NASA has implemented measures to extend their operational lifespans. Over the past few years, non-essential components and heaters have been deactivated to conserve energy for the probes. It's a strategic move that ensures that the Voyagers can continue functioning well into the next decade, and the estimated mission end date is 2030. The culmination of the Voyager missions evokes bittersweet emotions for the scientists and engineers who have played critical roles in this extraordinary journey since its inception. Their unwavering dedication and tireless efforts have carried the project far beyond its initial expectations. The data transmitted by the Voyagers has yielded invaluable insights, propelling countless scientific discoveries and fueling the imaginations of researchers and space enthusiasts across generations. It's important to note that Voyager 1 and Voyager 2 were not your regular spacecraft. They were meticulously designed to be stable platforms. Their rotation rate is more than 15 times slower than the hour hand of a clock. This deliberate design choice minimized any blurring of images and data as the spacecraft zoomed through space. Scientists and the general public never ceased to be astonished by their impressive imaging capabilities, even before their encounters with the outer planets. The spacecraft began beaming back images of Jupiter, while still several months away from the planet. These early images, showcasing the swirling clouds and the famous Great Red Spot, brought sheer delight to the people at NASA's Jet Propulsion Laboratory. But it was the discovery of active volcanoes on Jupiter's moon, Io, that stole the show. It is a little bigger than Earth's moon. But the amazing thing is that it turned out that there's no volcanic body in the entire solar system as active as that moon. The spacecraft's instruments detected some peculiar signals emanating from Io, and the vivid images they captured confirmed the findings. Those images revealed towering volcanic plumes and a surface marked by the ejection of volcanic material. One of Io's prominent volcanoes, Peel, has even erupted 30 times higher than Mount Everest, blanketing an area nearly as big as France. In total, The Voyager spacecraft snapped over 33,000 images of Jupiter and its moons, revealing the planet's stunning beauty and the incredible diversity of the Jovian moonscapes. Before we dive into the recent mind-boggling discovery, let's not forget that the twin Voyagers have been uncovering breathtaking findings since their launch. One of the most astonishing revelations was the existence of Jupiter's rings, which, although faint, added an extra layer of intrigue to the gas giant. On top of that, Voyager 2 unveiled the icy shell of Europa, one of Jupiter's 53 moons, believed to be over 60 miles thick. These findings challenged our previous assumptions about these far-off celestial bodies and sparked further investigations into the potential habitability of icy moons. As the Voyagers bid farewell to Jupiter, they received a gravity assist that gave them a vital boost, propelling them toward Saturn. Without this nifty push, they wouldn't have escaped the sun's gravitational pull and ventured deeper into space. Voyager 1 and Voyager 2 then went their separate ways, each heading towards new frontiers. Voyager 1 embarked on a trajectory that brought it close to Saturn's moon, Titan, enveloped in an orange, hazy atmosphere. The mysteries surrounding this moon piqued the interest of scientists, leading to more studies on its complex chemistry. Voyager 1 then veered northward, departing from the plane of the planets, and began its epic journey beyond the boundaries of our solar system. Meanwhile, Voyager 2 embarked on a series of thrilling adventures that took it to the outermost planets of our cosmic neighborhood. In 1986, it made history with a flyby of Uranus, where it stumbled upon 10 previously unknown moons, increasing the planet's moon count. 3 years later, Voyager 2 reaches Neptune, unveiling the extraordinary features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, making it the fastest wind ever observed on a planet within our solar system. As the spacecraft zoomed within 280 miles of Neptune's azure, methane-rich atmosphere, it provided unprecedented insights into this remote world. Neptune's largest moon, Triton, turned out to be one of the chilliest spots in our solar system, with surface temperatures plummeting to a bone-chilling -235 degrees Celsius. Triton also boasted unique characteristics, including ice volcanoes that spewed nitrogen gas and icy particles up to 5 miles high into its thin atmosphere. These discoveries expanded our understanding of the incredible variety and complexity of celestial bodies, even in the farthest reaches of our cosmic neighborhood. One individual who played a pivotal role in extending the missions beyond their initial goals was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing one last set of images before shutting down the cameras on both spacecraft. These images would serve as a parting gift to humanity, offering a final glimpse of our home planet from the distant depths of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back towards the inner solar system and snapped a series of 60 images. The most iconic among them, known as the pale blue dot, remains an indelible symbol of our place in the cosmos. Taken from a staggering distance of 38 billion miles, it stands as the farthest image of our planet ever captured. Earth appears as a minuscule, pale blue speck, barely discernible amidst the vastness of space. At the heart of the Voyager mission lies an extraordinary relic: the enduring 8-track tape. Picture it as a time-traveling artifact, a treasure chest filled with invaluable scientific knowledge, hurtling through the cosmos. The 8-track tape recorders used on the Voyager probes were not your typical consumer cartridge tapes. They were a reel-to-reel storage system designed by Lockheed and manufactured by Odetics Corp. These machines were quite impressive in terms of their specifications. They used a belt-driven mechanism and employed a 76-foot-long reel of 12-inch wide magnetic tape. The tape had 8 separate tracks for recording data. The recorders had 2 different recording speeds available: 115.2 kilobits per second and 7.2 kilobits per second during playback. The maximum speed was slower at 57.6 kbps, but there were also options for 33.6, 21.6, and 7.2 kbps playback speeds. You might be wondering why there are only a few expeditions as successful as this mission. It's time to get into that. While the space probes have seen wide success in their mission, the journey wasn't exactly as smooth as it seems. Threatening situations. Is Voyager too lost? By consensus, no space mission has made an enduring impact on our understanding of the universe as much as the Voyager probes. The mission was solely dedicated to exploring our solar system, but the Voyager probes decided to kick it up a notch by exceeding all expectations and venturing into uncharted regions of space. The scientific community has remained fascinated by Voyager 1's remarkable journey, providing a lot of valuable data about our cosmic surroundings. Today, 5 decades after its monumental launch, the Voyager mission continues to hold the record as the longest-running mission conducted by any space agency in the world. Astonishingly, this space probe has defied initial predictions, which estimated its lifespan at only 5 years. The difference in duration is truly remarkable, from 5 years to almost 50 years. However, while people celebrate the probes, what many people are unaware of is that Voyager 1 narrowly escaped a mission failure. It encountered a major setback during its launch when one of the rocket stages malfunctioned, requiring significant last-minute adjustments to prevent mission failure. NASA's engineers didn't sit, though, offset. They quickly responded with their expertise, eventually resolving the issue and allowing Voyager 1 to catch up with, and even overtake, its twin probes in space. NASA's Suzanne Dodds and his team transmitted a routine command to Voyager 2 on July 21. And that was when the unthinkable happened. They accidentally sent the wrong version, which pointed the interstellar probe's antenna slightly away from Earth. As usual, the scientists expected to receive data. However, they heard nothing at all. This seemingly small error almost made humanity lose its connection with the popular spacecraft, now 12.4 billion miles from home, along with its twin, Voyager 1. Humanity's farthest-flung spacecraft is still collecting data. The team settled on a solution: blast a shout command in the probe's direction, telling it to adjust the antenna and point it back towards Earth. The craft could still receive the signal, even though its antenna was already offset, if the signal was strong enough. They carried it out on the morning of August 2, sending the highest power signal they could by using the high elevation 70-meter, 100 kilowatt S-band transmitter at the communication station in Canberra, Australia. The station is part of NASA's Deep Space Network, an international system of giant antennas managed by JPL. There was no guarantee of success, and it would take 37 hours to see if the solution had worked, or if they had to find another way before the Voyager was lost forever. Unsurprisingly, the entire team spent a sleepless night waiting and hoping. And then, there was finally some relief. It worked. Contact was restored on August 3 at 9:30 p.m. Pacific Time. They went from "oh my God" to "thank God." If, by any chance, the attempt had failed, the team would have only had a single backup option left: the onboard flight software's fault protection routine. Multiple fail-safes were programmed into the Voyagers to automatically take actions to deal with circumstances that could, in any way, harm the mission. The next routine was expected to kick in mid-October. If it worked, it would have generated a correct pointing command, hopefully adjusting the antenna in the right direction. Now, while the NASA team restored communications with their beloved spacecraft, it won't be the last scare they will be given. The Voyagers have aged well past their prime, and their dwindling power means that their scientific instruments can be run for only a few more years. The Voyager probes are powered by radioisotope thermoelectric generators, which convert heat from the decay of radioisotope fuel, plutonium-238, into electricity. But unfortunately, fuel sources have been decaying for a long time. To conserve what little power they have left, the Voyager team has already shut down the heaters for all the scientific instruments, which have continued operating normally despite that. In the coming years, the magnetometer, plasma wave surveyor, and charged particle detector will likely have to be shut down, one at a time, to ensure a few more years of interstellar science. Everybody was exuberant that they had the spacecraft back, but it also made them realize that this mission could end any time, whether a human error was involved or just because the spacecraft was old and broken. It makes you value what you have. The probes can't just rely on their inbuilt devices, so NASA came up with ingenious ways to help them in their mission. Touring space for half a century, the launch of the twin spacecraft happened almost 50 years ago. In August and September 1977, they were saddled with the heavy responsibilities of exploring interstellar space. To achieve these goals, these resilient spacecraft employed a clever technique called gravity assist maneuvers, which played a crucial role in their legendary missions. Think of it as a cosmic dance between the spacecraft and the massive planets of our solar system. Instead of relying solely on their inbuilt engines, the Voyagers utilized the gravitational pull of these giant planets to catapult themselves toward their original destinations. This ingenious maneuver not only conserved fuel, but also provided the necessary velocity to visit multiple destinations on their grand tour. Gravity assistance, also known as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it passes by. For better understanding, consider Voyager 1 approaching Jupiter, a colossal gas giant with an equally immense gravitational force. With complete precision, Voyager 1 was strategically guided to zoom past Jupiter at just the right angle and speed. Jupiter's gravity then pushed the spacecraft, giving it a significant velocity boost and essential cosmic oomph. However, executing this maneuver requires intricate art. If Voyager 1 had approached Jupiter at the wrong angle or speed, the result would have been disastrous, as it could have resulted in a catastrophic deviation from its intended course, even though the level of precision required by this maneuver is almost unimaginable. The brilliant minds at NASA's Jet Propulsion Laboratory successfully choreographed these celestial ballets, not just once but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. For instance, Voyager 2 utilized gravity assistance from Jupiter and Saturn to reach Uranus and Neptune, making the grand tour possible. One could say that the Voyager missions may not have been so seamless, but for these slingshot maneuvers. Voyager 1 went on to reach interstellar space, and Voyager 2 swiftly followed suit, all thanks to the precision of these gravity assists. The concept behind gravity assists may appear straightforward, but their execution is astoundingly complex. Voyager 2's grand tour demanded meticulous precision, as missing any of these slingshots could have jeopardized the entire mission. Despite the inherent risks, the team at NASA successfully navigated Voyager 2 past Jupiter, Saturn, Uranus, and Neptune, achieving a feat unparalleled in the history of space exploration. The Grand Tour was a testament to human ingenuity and the spirit of exploration that drives us to push the boundaries of our knowledge. As Voyager 1 and Voyager 2 continue their odyssey through interstellar space, their journeys stand as enduring monuments to human curiosity and the relentless pursuit of knowledge. From their groundbreaking discoveries within our solar system to their historic entry into the uncharted territory beyond, the Voyager probes have transformed our understanding of the cosmos and inspired generations of scientists and explorers. With each passing year, as they venture farther from home, these intrepid spacecraft continue to captivate our imagination and remind us of the boundless possibilities that await us among the stars.